Hey, what's up guys? This is Dr. Vivek Palipuram bringing you the next lecturette in ECPE 127. In this lecturette, I'm going to introduce you to some other topics in joint random variables, and those are expected values when we consider joint random variable, covariance, correlation, and independence. We have already spoken about independence, but we'll see more into independence with respect to how it affects the value of covariance and correlation. So before we proceed any further, I would like to discuss this problem that I had given to you in one of my previous lecturettes. Specifically, I asked you to find the marginal PDFs of x and y and tell me whether they are independent or not. And I also asked you what's the probability that x is less than or equal to y and the probability that x plus y is less than or equal to 1/2. Now, most of the class was in general in the correct direction, but we actually missed with a little bit with respect to the limits of the integration. So let me solve this problem for you guys one more time, or rather I have not solved this before, so let me solve this problem for you. In this problem, we have already found the value of C as 2. So with that, let's find the marginal PDFs of x and y, because I think that's where most of the people or most of the students have gotten it wrong. Students were fairly good at calculating these two probabilities. So in general, I am happy with the performance, but let's practice as to how to find out the limits of integration appropriately. So the f of x comma y, the joint PDF, is given by 2 for x greater than or equal to 0, y greater than or equal to 0, and x plus y is less than or equal to 1, and it is 0 otherwise. So this is the region over which the joint PDF is non-zero. So that's going to be the region of non-zero probability. So let's plot it. So this is the region of non-zero probability right here, all the points under this line. So this point is 0, 1, this point is 1, 0. So all of this region is the region of non-zero probability NC. I asked you to first calculate the marginal PDF of x. So when you calculate the marginal PDF of x, the usual way is to integrate the joint PDF from -∞ to infinity with respect to the other random variable, y in this case. However, for this particular PDF, the limits of integration is now going to change. I'm going to integrate the joint PDF, which is 2, or this region with respect to y. So let me find the limits of integration, and here's how I'm going to find it. So for any value of x, y varies from 0 all the way to this point where y is 1 minus x. So that's the limit of integration from 0 to 1 minus x. Now, because I integrated y out, the y term is going to disappear from the region of non-zero probability. So y term disappears, and all that I'm left with is the marginal PDF of x, which is 2 times 1 minus x for x greater than or equal to 0, but x is less than or equal to 1, essentially for x between 0 to 1. And it is 0 otherwise. So that is the marginal PDF of x. In fact, many students have gotten it right. Now, when we evaluate the marginal PDF of y, this process is going to start all over again. Many students, they continued from here onwards, and then they decided that the limits for x will be from 0 to 1. That is incorrect. When you calculate the marginal PDF, the process starts all over again. So when I would like to find the marginal PDF of y, I'll again evaluate the region of non-zero probability and perform integration or the region of non-zero probability. So this is the region of non-zero probability, and this time I integrate with respect to x. So when I integrate with respect to x, I integrate the joint PDF with respect to x. This is the region of non-zero probability for the original joint PDF. Now let's find out the limits of integration. So for any y, x varies from 0 all the way to this point where x is equal to 1 minus y. So notice what I have done here. I have restarted my limits of integration, or I have restarted this integration process because I'm not evaluating any double integral or what have you here. Evaluation of marginal PDFs is always single integral when you consider two random variables. So here the limits will be from 0 to 1 minus x, or rather from 0 to 1 minus y, 0 to 1 minus y. So f of y will be 2 times 1 minus y. Now because I integrated x out, x will disappear from the joint PDF, and all that will be remaining is the marginal PDF of y, which is valid for this region, which is essentially y is less than or equal to 1 but greater than or equal to 0, and it is 0 otherwise. So this is how you're going to evaluate the marginal PDFs. When you have two random variables, you perform single integration to evaluate the marginal PDFs, and each time the integration is going to reset. So you will evaluate fresh limits of integration here, unlike double integration, which I'm going to show you next when I calculate the value of probability that y is less than x, or rather x is less than or equal to y. So let's focus on evaluating the probability that x is less than or equal to y, less than or equal to capital Y. So this is the region of non-zero probability right here. X is greater than or equal to 0, y is greater than or equal to 0, and x plus y is less than or equal to 1. So this line is x plus y equal to 1. I need to find the probability of this region A. So let's plot this region. This is step 1, plotting NZ. We plotted NZ. Now step 2 is to plot A. So let's plot A here. So A is x is less than or equal to y. In order to find this region, let's first plot the equality relationship, which is this line right here. So this line is x is equal to y. And I need to find out the region x is less than or equal to y. To find this region x is less than or equal to y, what I'll do is I'll identify some arbitrary coordinates in this space. So this is 0, 1 and this is 1, 0. Clearly 0, 1 satisfies this condition where y is indeed greater than or equal to 1, or greater than or equal to x. So this is the intersection between NZ and A. So step 3 is to plot an intersection between NZ and A. In the maroon shaded area that I just shaded, that's your NZ intersection A. Now this intersection is going to help me find the limits of double integration. So to find the probability that x is less than or equal to y, I need to evaluate the double integral of 2, which is the joint PDF with respect to y, then with respect to x, or the region of non-zero probability. So I'll evaluate, or I will identify the limits of integration for this shaded region. So let's do that. So in this region, let's identify what this point is right here. At this point, both of these equations, x plus y is equal to 1 and x is equal to y, hold true. So both of these equations hold true. So let's find out what the value of x is. X will be equal to 1/2. You can prove that. X is equal to 1/2 right here. So my limits of double integration will be obtained as follows. For any x, y in this region varies from this point where y is equal to x all the way to this point right here where y is equal to 1 minus x. So that's the limit of inner integration with respect to y. For any x, y varies from x till 1 minus x. So from x till 1 minus x. Once I have integrated y out, once I have disregarded y now, x varies from 0 till x is equal to 1/2 in this region. So x goes from 0, but it never exceeds 1/2 in this region. So 0 to 1/2. Now, whenever you have such a setup for double integration to find the probability, always make sure that the outer limits of integration involve constants. In that way, you will always get a constant value for your integration. So let's solve this integral here. So let's solve this integral. I get 2 times 1 minus x dx from 0 to 1/2, and when I finally solve this, I get x cubed over 3, 0 to 1/2, and you can plug in the limits and you can find the value of this integration. So that's how you solve for the probabilities of different regions. So in general, when we evaluate the double integration to find the probabilities of a given region, this is going to be how you're going to identify the limits. After you have identified the region of non-zero probability intersect A. So you have f of x comma y, let's say dy first and then dx. So these limits will be for any x. For any x, find out how y is varying. So for the inner integral, this is how you're going to identify the limits of integration. For any x, find out how y is varying. In our case, it was from x till 1 minus x. Then for the outer integral, you have something like this. The lower limit of the integral will be minimum value of x in that region, minimum x in that region. In this case, the minimum x is equal to 0, all the way to max x in that region. In that case, it is equal to 1/2. So that's how you solve or you identify the limits of integration when you would like to find the probabilities of different events. When you integrate with respect to y, the limits will be for any x, find out how y is varying, and then the outer integral will be minimum value of x till the maximum value of x in that region. Now similarly, I can identify the probability that x plus y is less than or equal to 1/2, something like this. So this was the region of non-zero probability here. And let's say that I need to find the probability that x plus y is less than or equal to 1. Let me use another pen for shading that region. Let's say that I use green. So this is that line x plus y is equal to 1. So this is the region in Z intersection A. So when I find the limits of integration, let's say I integrate with respect to y first. So for any x, find out how y is varying. So in this region, for any x, y varies from 0 till 1/2 minus x. That's how y is varying. Then for outer integral, the limits will be from minimum x to maximum x. X in this region is minimum at x is equal to 0, and it is maximum at x is equal to 1/2. So those will be the limits of outer integration. So you are going to use this methodology to identify the limits of integration. Now, if you carefully observe here, in order to find the marginal PDFs, I can also try to generalize how to identify the limits of integration. And let me generalize it for you. To identify the marginal PDFs, let's say f of x, I need to integrate with respect to y. So you'll find out the limits as for any x, find how y is varying. And similarly, when you find f of y, this integration process starts all over again. And you'll ask yourself for any y, find how x is varying. So these will give you the proper limits of integration. Okay, so moving on. Next, let's discuss the expected value and some other statistical terms like covariance and correlation and independence, which occur frequently with joint random variables. So the concept of expected value is a simple extension from single random variables. So expected value of any function of x and y is given by double integration of gxy times f of x comma y with respect to x and with respect to y. You can also switch the order of integration if it leads to simplified limits. I can also perform it with respect to y first, then with respect to x. I like to perform with respect to y first. Then there are some properties with respect to the expected values. So for example, expected value of a1 times g1 plus a2 times g2 and so on can be written as expected value of a1 times or a1 times the expected value of g1 then plus a2 times expected value of g2 and so on and so forth. That's simple because double integration term can be distributed to these individual items. Then similarly, expected value of x plus y is equal to expected value of x plus expected value of y. Variance of x plus y is equal to variance of x plus variance of y plus 2 times this big term here. What I would like for you guys to do is try to prove it mathematically that this statement holds true. That's for your practice. Covariance happens to be one of the very important terms when we discuss joint random variables. So covariance of two random variables x and y is given by expected value of x minus mu of x times y minus mu of y. So the covariance term essentially tells us how x and y are growing with respect to each other. So for example, if this covariance term is positive, then it gives you this information. If you find that x is less than mu, then y will also be less than mu in order for this covariance relation to be positive. Similarly, if x is generally greater than its own average, then you can also expect that y is also greater than its average. So both x and y, they're increasing or decreasing in the same direction. But when covariance of x and y is less than 0, however, then you say that both x and y are increasing or decreasing in opposite directions. You can expect them to have opposite signs. Both x and y are said to be correlated if the covariance of x and y is exactly equal to 0. In such a case, you cannot really tell whether both of them are increasing or decreasing with respect to each other or not. It's very hard to tell. That means that they are uncorrelated because their covariance is equal to 0. However, if let's say for some reason x and y have radically different units, you may find that the covariance of x and y may be approximately equal to 0. Then in such a case, you may ask yourself, how do we analyze that? Do we say that x and y are uncorrelated? Not quite. X and y, the covariance of x and y has to be exactly equal to 0 for them to be uncorrelated. But when the covariance of x and y evaluates to approximately equal to 0, there's some other statistical measures we tend to use to find out how x and y are distributed with respect to each other. And that term is the correlation coefficient. So the correlation coefficient of two random variables is given by this formula here. Covariance of x comma y, or sigma of x times sigma of y. So notice that this term right here, rho of x comma y, the correlation coefficient, is actually a dimensionless quantity. And its value is going to be between -1 to 1. If rho of x comma y is very close to 1, then you can say that there's a strong linear correlation between x and y. So if you were to find the distribution of x and y, they are quite linearly correlated. If rho of x, however, is less than or its negative value, let's say it's approximately equal to -1, then that means this is the data distribution of y with respect to x. So they are negatively correlated to each other. However, if x and y have a correlation coefficient approximately equal to 0, then that means both x and y, they are uncorrelated. Meaning that you cannot devise a relationship between y and x or you cannot devise a mathematical relationship between y and x to distribute, or rather to describe one variable with respect to the other. So that's correlation coefficient. Then there's another term called the correlation. So correlation of x and y is given by expected value of x times y. This is usually used for statistical signal processing concepts to find out whether x and y have this tendency to cancel each other out. If x and y tends to cancel each other out, the expected value of x times y will be equal to 0. There is some weird terminology with respect to covariance and correlation. We say that two random signals x and y are uncorrelated if their covariance is 0. But when their correlation term is 0, we say that the two random variables are orthogonal. So it seems that these terms were devised by some really confused statisticians. And unfortunately, we'll have to live with it. So when two signals are uncorrelated, that means that their covariance is 0. And when two signals are orthogonal, that means that their correlation term is equal to 0. You can also explain the concept of independence or exploit the concept of independence to find out the values of covariance and correlation. Two random variables x and y are said to be independent if their covariance is equal to 0. When covariance of x and y is equal to 0, it essentially tells you that one random variable does not clearly tell you whether the other random variable is increasing or decreasing. They are absolutely uncorrelated. Now, because they are uncorrelated, they are also independent. So when covariance of x and y is equal to 0, you get the fact that x and y are equal to 0. And in such a case, when x and y are independent of each other, variance of x plus y is equal to variance of x plus variance of y. Now these two items are really very important when you are trying to explain multiple phenomenon, or you are trying to explain phenomenon comprising multiple random variables. When there is reasonable grounds for assuming that the random variables are independent, these simplified equations help us to perform quite straightforward analysis. I'll stop my lecturette right here. So this lecturette served to solve some more problems with marginal PDFs, with finding the probabilities of different events for joint random variables. And this lecturette also introduced you to some other statistical concepts such as covariance, correlation, and how to deal with independence of two random variables, and how to calculate the values of covariance and correlation when two random variables are independent of each other. So we are going to stop this lecturette right here. In the next lecturette, I'm going to solve problem number 1 for you. Specifically, I'm going to focus on this particular item because I would say that this one is the difficult of the two problems. And then I'll have you solve this problem on your own. And then I'm going to give you another problem which you will submit as in-class participation problem for Monday's class by 5 p.m.